Hey everybody, it's Miss Smith. So today we are going to start forces in two dimensions. Now everything that we have done so far has been on a flat plane. And so we've done free body diagrams all at 90-degree angles. And so the calculations are very simple. You add, subtract, it's easy when you're trying to find net force. What happens if you are no longer on a plane like this and you're on a plane like this instead? Okay. Oh, it's going to get rough, okay? So what I've decided to do is I'm actually going to take it very slow instead of me just throwing the concept at you and saying, here's all the steps, do it all in order. I'm going to go very slow with this because this is one of the hardest concepts of the whole year. So it actually takes a lot. And when we finally get to the end of this and we start doing full-length problems, normally in my classroom, that big whiteboard I have, I would fill up the entire whiteboard and one problem would take 30 minutes. And that's also 30 minutes of me explaining it. Myself, when I do these problems, it takes me about 5 minutes. But I know how to do it, so that's still a lot. But anyway, you will be okay. I know I'm not helping you at all. You're probably terrified of what we're going to learn today. Today, we're just starting off with free body diagrams of an inclined plane. So this is fine. You will learn this. You will get this down. Now, remember that free body diagrams are supposed to help you because when we start doing these, when you write things for a net force, because net force does not have a given formula. Okay, it never does. Just, I know that net force is mass times acceleration, but that's in terms of acceleration. What I'm talking about is net force in terms of all of the forces in a system. Okay, so a formula for a net force, overall net forces, is not written. You have to write it. Okay, and so I'm going to teach you how to do that today. So again, I don't mean mass times acceleration. I mean the forces acting on an entire system and the overall force with all of those put together. Sometimes you subtract, sometimes you add, sometimes you have to square it. It's crazy, but I'm going to show you how to do that today. So that's all we're doing. We're just doing free body diagrams today. And I'm going to show you how to write those formulas. So that's very simple. I normally, in a regular classroom setting, I spend about 5 minutes on that, and then I move on. So I want to make sure that you get it. If you don't get it, you need to tell me, okay? I'm not sitting there with you. I can't watch you to see if you're not getting it, okay? You have got to tell me. If you're like, hold on, I have no idea what you're talking about, stop what you're doing, send me a message, okay? If you've got to replay my video 15 times, do what you got to do, okay? Nobody's judging you, all right? I want to help you get a good grade as much as you can, but I also have to make you responsible of your own learning, okay? And you know this, we've talked about this, okay? Use me as a resource. I can help you. We can do one-on-one tutoring sessions. I can do a video call with you. If we've got to do it, that's fine. I don't care. Let's do it, but you got to tell me, okay? So you're going to be just fine. It's just going to take some work on your part, but you will be okay, I promise. So we're going to call this free body diagrams two-dimension or 2D. So everything that we have been doing up until this point for free body diagrams has been something along these lines. Everything's 90-degree angles of each other. All right, and it's because something is, here's your X, and here's your surface here. You've got your object here. You have a normal force, gravitational force, force this way, force this way. Okay, everything's been flat, okay? But now we are going to do things where we are on an inclined plane. So something like this. So let's say that we have a nice little box sitting on this inclined plane, okay? Now, we need to set up our coordinate plane. Okay, I need you to understand kind of where the origin is and stuff like that. So now I'm not going to set up a official coordinate plane. What I am going to do is tell you where your surface is, like the normal flat surface that you're usually walking on. That's going to be here. All right. Now, what's important is this angle right there. We're going to call that angle theta. So we're going to call that angle theta. Now, so let's say the scenario is a box is sitting on an inclined plane and it starts to slide down. Down's important. Don't forget that word, down. Starts to slide down the inclined plane. And the question will ask you, it could be various questions. What's the frictional force of this box, acting on this box? What's the net force acting on this box? What is the acceleration of this box down the inclined plane? That's the big question. That's the one that takes a while, is finding acceleration down the inclined plane. So it doesn't matter what's going on. It's always a good skill to find the net force. Okay? No matter what you're doing, find the net force. It will help you. So what I'm going to do is let's draw the free body diagram for this box. Okay? Now, I'm going to do this in this blue color. Everything has gravity acting on it always. So it doesn't matter if it's on a hill, if it's flat, whatever it is, if it's on the earth, it's got gravity acting on it. So I'm going to put a dot in the center of this box, and then I'm going to go straight down for gravity. Okay, and I'm going to label that Fg. That is the force of gravity. Okay, I'm going to put a little key down here so you know what each of these means. I was going to say force due to the acceleration of gravity, but I'll just say force of gravity. That's what I'm going to say. All right, now, we know that normally if we're sitting on a flat surface, and let's say we have a box that's sitting here, we have gravity acting downwards, and we would always say that normal force, since it's touching a surface, is acting opposite of gravity. Okay, so whenever I taught this, I may not have said this, and because it gets a little funky when I teach this originally when we talk about normal force. In a normal situation, in a normal situation where you're on a flat plane, you're not on an inclined plane at all, and everything's flat, normal force is opposite of gravity. That's true. But when it's not on an inclined plane, things are a little bit different. So, normal force is actually opposite of the surface. Now, I know I said that if you're touching a surface, you have normal force. So normal force depends upon your surface. This is going to be normal force. So normal force is opposite of your surface. All right, so my surface is this. This is my surface, and here's my box sitting on the surface right there. So it's going to be opposite of my surface, so it's going to come off like this, and that's going to be Fn. Okay, it's perpendicular to the surface. So I guess a better way to put that, perpendicular, and this is the symbol for perpendicular, perpendicular to the surface. Now, what we've got to do is, because normal force is no longer straight up and down, like we learned yesterday, normal force now has x and y values. Okay? We now have to calculate those because this is not straight up and down or left and right anymore. It's at an angle. So I have to find these x and y values. Now, we discussed how in the past that gravitational force is equal to normal force. Okay, equal but opposite, Newton's third law of motion, equal but opposite. So just to make things a little bit easier on us, I'm actually going to do the drawing of normal force for x and y components down here. We're going to do this in terms of gravity. And that's okay to do that down here because remember, gravitational force is equal to normal force. Okay, that still stands true. Even if it's on an inclined plane, that still stands true, that they are still equal but opposite. So let's draw this out. This is where everybody gets a little funky. Okay, so you need to bring down your y value like this. Just opposite of, just straight up opposite of your normal force. Okay, And then you're going to bring in your x. All right, so let's go ahead and let's label these. I'm going to zoom in. So this is f g of y. This is f g of x. Now these are labels that we established not too long ago. So f g of y is the force of gravity in the y direction. And f g of x is the force of gravity in the x direction. All right, now here's your little right triangle right there. And your angle. Okay, now here's the important part. Angle theta, which is this one here, will be the exact same angle here. Exactly the same. I'm even going to use the same symbol. Angle theta. So if this angle here was 25, then this one is also 25. Now, there is a third angle that we may talk about, and that's this angle here. That's called angle, that's going to be angle phi, or phi, phi. But we're not going to deal with that angle right now. We don't need to discuss that. But these two angles are the same. They're both theta. For now, that's all you've really got to know at this point. So just to, let's stop and recap for just a second. Okay, so we did normal force. We decided that normal force was opposite of my surface. Okay, so perpendicular to my surface. So if you're having a hard time remembering how to draw this, remember that, so look at here, here's the perpendicular symbol right there. Okay, normal force is perpendicular to the surface. Now what you do is you bring out the y value. We brought it out like this. Now some of you may have difficulty drawing this. Excuse me, I did something incorrectly. I can't believe I did this. This x should be, that's why I was like, what is going on? Okay, I brought my y value down a little bit too much. I forgot that the right angle is supposed to be here, technically. There we go, that's better. Now that makes more sense. Here's the right angle here, so this would be phi. All right, so, excuse me, y'all, I'm sorry. It's been a hot minute since I've done this. Okay, so then this would be fg of x, and that one is fg of y. Fg of y is here, is fg of x. So let's zoom in, let's look at this a little bit closer. All right, so the issue that I've seen a lot of people make is when they draw this, they don't bring their fg of y out too far. They'll do this number and then connect it down there. Where the x and y meet, there's supposed to be a right angle, and that's a little bit of information that I forgot. There's supposed to be a right angle here where x and y meet. That was my fault. Anyway, so you've got to make this long enough, and so where this meets, it's got to connect with the end of fg over here, and it has to be a right angle here. Okay, so I get a lot of people that make this too short and try to do this. That is not a right angle. Or you did like me when I did the first time and make it too long and you're trying to do something like this or like this, like that. No. Okay. I made that mistake too, so it's easy. But anyway, so when you do this, you've got to have a right angle where x and y meet. You've got to have this right angle. That's important. Okay, so we don't need to know that this is angle phi. We don't need to know that at this point. You just need to know how to do this. So you're going to extend that straight out from your y, from your normal force. This is the fg of y. You extend that straight out from your normal force, fg of y, and then fg of x will make a right angle with fg of y. Okay? So that's the basics of knowing which one is which. Now, let's look at some other forces. So we did that. We took care of gravity. We took care of normal force. That's the basics of what needs to be done. Now, at this point, you would be pretty close to done if the box wasn't moving, okay? If the box wasn't moving, I would have a little bit of static friction going this way. I would have just a little bit of static friction, just enough to hold the box sitting there because it has to counteract its weight. So you have a little bit of friction this way because what happens, this vector right here is what's pushing the box down. Okay, if you notice, these two are parallel to each other. When we drew this, these become parallel to each other, which means that they are acting together. Okay, so this is the same angle as this right here when we drew this, so that means that they are acting together. So this vector, that fg of x, is what's actually pushing the box down the incline. So in order, remember Newton's first law of motion, if I have a force, if an object in motion will stay in motion unless acted on by an outside force. So if I've got this x value pushing it down the incline like this, but yet this box is not moving at all, it means that I must have something going opposite this way. Okay, and that's static friction. Okay, so you would have a little angle here. It would be equal but opposite of my fg of x, equal but opposite, because fg of x would be going down the incline. So they would be equal but opposite. Now, we said that the box was moving. So that means since I am moving, that means that I have a net force going down the incline. Now, I don't know how big this net force is. I'm just going to draw F net. So that's for net force. And that's going to go down the incline. So whenever you would have to actually calculate net force, you would have to give a direction to net force and say it's going down the incline. You would say 25 newtons down the incline or down the slope or something along those lines. Now, in this particular scenario, I said that the box was sliding down the incline. So that means that we are going to have friction. I didn't say anything about neglecting friction. Now, for the most part, anytime we do one of these problems, we are going to neglect air resistance. So because it's such a small value, just forget about air resistance, okay? It's the friction that's the one that's kind of decides what we're going to do. Now, in a perfect world, every single thing has friction. But when we do calculations, next week when we start getting into calculations and start putting numbers with all of these letters, I will teach the scenario without friction first because the calculations are a little bit easier if you don't have to include friction. So I'll teach you without friction first, and then the following day I will teach you how to do the same thing but including friction. So the first day will be without friction, which is not a realistic situation, but we've got to get these calculations down first before we get into the hardest scenario that includes friction. So that'll be next week. So now let's go ahead and let's draw friction, and because it's moving, that means my frictional arrow is small. This is going to be FF for frictional force. All right. Now, let's review why I knew that this arrow was small. Okay, had I had this arrow equal here, they would have come out and been equal this way and this way, equal but opposite. Then this box would have not been moving. No movement at all. Okay, but because it is moving, then I've got to have a small arrow here. Now, it would be very good practice for you to go ahead and draw your fg of x up here so you don't forget about it. Okay, so if you wanted to draw that up here so you don't forget about it, you could do like a second arrow. I like to come out a little bit so I can label them. Well, I'm going to come out a little bit. I'm going to come down here, fg of x. Now, these vectors are not to scale. Okay, so from this point, I would like to write the net force formula for this. Okay, this is where it starts to get a little nuts. And this is what I was talking about, how The formula for a net force, when you're including all the forces in the entire system, which is what this is, all the forces in an entire system, when you're writing the net force formula, it is specific to the question. Okay, because you could have something being pulled up the incline. You may have somebody tumbling down the mountain. I don't know. But it's specific to the situation. So you've got to read the problem and decide what to do. This is the reason why law sines and law cosines was so important, was what happens if we don't have a right triangle. So you'll have that skill if that does happen. Now, let's go ahead and start writing this formula. So I'm going to write this in this red color. So I need to have F net. So basically, what you're going to do is look at all of the vectors that we have. So this is why this is so important that you draw this, because this is really hard to keep straight in your head if you don't draw it. So what you do is you look at this drawing and you can kind of cancel out vectors. So let's look at normal force versus Fg of y. Those are canceling each other out. So I'm not really worried about that in terms of net force. Now, when we start calculating friction, remember friction depends upon how hard it's pushing on a surface. We would have to use Fg of y. That's the only time you really use Fg of y is if you're calculating friction. But that has a formula written for it, and I'll give you that formula. That is next week, okay? So when you're calculating net force, however, just in the general formula for net force, these are equal but opposite. So I'm not going to include that in my net force calculation. Now, what I will do is I'm looking, now net force is everything kind of in this direction, because this is where my motion is. I've already decided that this way, these two cancel each other out. There's no motion going this way. I do have motion this way, of course. So that's what we're looking at, is this way here. So this has already canceled itself out. So we're not going to include that at all. So what's left, remember we brought this one up here. It's right here. Okay, so I'm not going to look down here for this one. I'm looking for this one. So what's left is Fg of x. So I'm just going to kind of write this off to the sides. Fg of x, we have F net, and we have F of frictional force. So those are the three that we have. So we need to look at what direction they're headed, because if they're in the same direction, then you add them together. But if they're in opposite directions, you subtract. Now, we are trying to solve for net force. So we're not going to include net force. We're not going to include net force in our calculation. So really we're only left with Fg of x and Ff. Now they're opposite, which means I need to subtract. So Fg of x minus frictional force. And there's your formula for that scenario. And that's it for net force. Like if you were asked to find the net force, that's all you have to do. But you have to go through the process of elimination. Do I include this force? Do I not? Okay, so let me give you another scenario. Go ahead and draw. I always kind of draw my inclined planes like this. Okay, so let's say that it's a ball. And you have decided, let's say you're rolling a snowball up a mountain, okay, for whatever reason. You're in the mountains with a bunch of snow. Some of you don't like the cold, so maybe you're not. Maybe it's a boulder that you're trying to get up a hill. I don't know. But everything's still going to act the same. So everything always has gravity acting on it. So we're going to do gravity straight down. Now look, a good exercise for you to do would for you to draw this at the same time as me. So here's the scenario before we go any further. This particular question is you are pushing a ball up the inclined plane. So whether it's a snowball or a giant boulder, whatever it is, you are pushing it up the inclined plane. What is the net force formula? That's the question. So we've got to get all of our forces decided on, and then we can do the actual calculation. Hold on, the bell's ringing. Okay, so we're going to go straight down. Force of gravity acts on everything. Now, the next thing that we do is normal force. Normal force is opposite or perpendicular to my surface. So there it is. Here's my surface. There's my surface. There's normal force. It is perpendicular. All right, now let's do the X and Y components. If you are on an inclined plane, you will have X and Y components. So I'm going to zoom in a little bit. The Y component will come straight down like this. Let me not make the same mistake I made last time. I need to have a right angle here. So let's bring this across like that. That's pretty close. Okay, there's my right angle. So this is going to be FG of Y. This one here is FG of X. Okay. So I'm going to put the arrows on these because this is FG of X is down the inclined plane. Okay. So let's see. So we're pushing this up the hill. So I'm pushing it up the hill. So I'm going to have an applied force up the hill itself. Now to go down, because my motion is up the hill, that means I'm going to have friction opposing my motion. Opposing means opposite. So I'm going to have a little bit of friction this way, so frictional force. And then remember, we're trying to practice putting our FG of X, because FG of X goes this way. Okay, remember FG of X is perpendicular, so it means that it works with this inclined plane. So we need to put FG of X. I'm going to bring this FG of X. I don't know if this is to scale. I'm just trying to get it in there. Okay, so now that we have labeled everything, we are now able to write the formula for net force. Now our net force, I'm going to go ahead and pull this out here. Our net force is going to be like that. So F net. So this way, these still cancel each other out. They still cancel each other out, so they are not included in my net force calculation. So net force, okay, and because we're making it equal to net force, we're not going to include this in our calculation. This is what it's equal to. So forget about this line for just a second, and let's look at the other three that we've got, these three. So F net is equal to applied force. Now, applied force is here. Oh, I just erased it. Wrong button. Applied force is here. These two are opposing applied force because they're in the opposite direction. So that means that you subtract both of them. Okay. And that's it. That's all for that one. Okay. Let's do one more type that you may come in contact with. All right, so we have a very large box here, very large box, and it is being pulled up the hill. There's like a little wheel right here that's pulling it up the hill. Okay, so let's draw the free body diagram. From the center, straight down, F, G. Perpendicular to the surface, F, N. Okay, so again, let me tell you the scenario before we move any further. This box is being pulled up the hill by a rope. So technically you would be down here at the bottom of this hill with a rope. Here you are right here at the bottom. And you're pulling this box up the hill. Okay, there's the scenario. So we already did gravity. That's straight down. We have normal force. It is opposite of our surface. So that means if we have normal force, it means that we also have FG of Y. If you have normal force in an inclined plane, we have FG of Y. So I'm going to pull this straight out, the same direction as, so this is actually an arrow. Same direction, but opposite of the normal force. Okay, so then here's FG of Y. This is a right triangle, right angle, and this is FG of X. Okay. Now, my up this way, where this rope is pulling it up, we're going to call this FT for tension. Tension on a rope. We're going to call it FT, and that's going up the inclined plane. Now, you are successful in getting this up the inclined plane, so that means that my net force is also up this in this direction as well. And then opposing that is Remember, we're trying to put this one, there's this one here. It's opposing motion. Fg of x. And then I have another one acting downward. It's just regular frictional force. All right, so let's write the net force formula. Net force, okay, so remember we've already canceled out these two. These cancel each other out, equal but opposite, so we're not putting these in this calculation. And net force is here, so I'm not going to include that in my calculation because that's what I'm trying to solve for. So I'm just looking at these three here. Now, F net is equal to F tension minus frictional force minus Fg of x. Now, they are both subtractions because you subtract frictional force and you subtract Fg of x because they are opposite than my motion. My motion is up here. Okay, now, you may have an issue deciding, are you going to go up the incline or down the incline? That will be listed in the question. Okay, now, sometimes you may be given a question that says, a force was applied to an object, let's say it was 100 newtons. A 100 Newton force was applied to an object up the inclined plane. According to the weight of the object, did you have enough force to move the box? You may be asked a question like that. So then you would have to decide, is Fg of x and the frictional force going to be more than the force that's applied? If it's not, then you have motion. Okay. Anyway, I know that this is probably a very foreign concept to you, and there's a lot of words and a lot of arrows, and you're maybe confused. I'm hoping that you're not. I hope I took this slow enough that you're okay. This may be one that you need to go to YouTube yourself and just kind of watch many videos about how to do this. So this is a free body diagram for an inclined plane. Is what you would put into YouTube. So a lot of it is just you need practice. You've got to see the same stuff over and over and over and over and over before you get it. So if you've got to watch, multiple YouTube videos that show you how to do it, then that's fine. Now, I am going to warn you though that sometimes they don't list things as FG and FN. You may see it listed like this, or you may see it listed like this. Okay, this is perpendicular. This is perpendicular. This is not P. This is parallel. Okay, so parallel forces versus perpendicular forces. Okay, so you may see something like that. You may also see something labeled like this. I mean, it doesn't really matter. You may also see something where it's not this, but this instead. Technically, that's the same thing. Force of gravity. Okay. The point is everything still works the same. It may just be labeled a little different. Okay, so if you need help, you know where to find me. I am going to warn you, however, it is important that you get this. You need to spend time making sure that you understand this. Because next week, when we get to the hard stuff, because this is not even hard yet, when we get to the really hard stuff next week, you will be lost. Okay? And it's going to, what we do in this class is we take one concept and we build on it and we build on it and we build on it until we finally get to our end goal. If you're not getting this stuff from earlier this week, you need to go back and make sure that you know how to do it. Because otherwise, when we finally get to the unit exam, you are not going to do well because you didn't take the time to make sure you know how to do those other concepts. So that's what I mean by make sure you take responsibility of your learning. That's the reason why I'm giving you the answers to the practice problems is so that you can check yourself. Don't go into that little mini quiz if you don't know how to do it. Don't do that. You check those practice problems. You do those practice problems and then you check your answers. And if your answers are wrong, message me. That's what that's for. That's the instructions that I have given you is if you have your answers and you look at mine and it's not correct, message me. Now, some of you have done that. You've done exactly what I've said, which is awesome. Congratulations. And you're doing well in my class. It shows that you're coming to me for help. But if you're not, I don't know what else to do. Okay? It's your responsibility to take care of your own learning.